Good morning, students. Welcome to video lecture on electromagnetic waves and transmission lines. Subject code U18EC403. Topic boundary conditions on B and H. Boundary conditions on magnetic flux density and magnetic field intensity. Condition 1, HT1 is equal to HT2 and HT2 minus HT1 is equal to K cross AN1, 2. HT1 is equal to HT2 means the tangential component of magnetic field is continuous across any boundary except conductor boundary, and HT2 minus HT1 is equal to K cross AN1, 2. This condition is for conductor boundary. The physical significance of condition 1 is the tangential component of magnetic field is continuous across any boundary except at the surface of a perfect conductor. And condition 2, Bn1 is equal to Bn2. The physical significance of condition 2 is the normal component of magnetic flux density is continuous across any boundary, or the normal component of magnetic flux density in medium 1 is equal to the normal component of magnetic flux density in medium 2. Here K is current sheet, units are ampere per meter. It is the current per unit length. It is the current deliberately placed at the boundary, and AN12 is the unit vector normal to the boundary directed from medium 1 to medium 2. Here it is medium 1 and medium 2. It is normal to the boundary directed from medium 1 to medium 2. Boundary conditions on H, magnetic field intensity. For that, consider a plane. It is the position of boundary. Consider a rectangular loop on the boundary. It is the boundary 0, 1, 2, 3, 4, 5 and 0. Now let it be medium 1 and medium 2. Magnetic field intensity in medium 1 is represented by H1. Its tangential component is HT1. Its normal component HN1, where H1 is the combination of HT1 and HN1. That is, the tangential component is in this direction. The normal component is in this direction. Now consider magnetic field intensity in medium 2. It is H2. Its normal component HN2 and its tangential component HT2. It is the direction of HT2 and it is the direction of HN2. And along the tangential direction, the length of the rectangular loop is delta x along normal direction. The length of the rectangular loop is delta y. And here the angle made by electric field with respect to the normal is theta 1 in medium 1, and angle made by electric field in medium 2 is theta 2 with respect to normal. And from Ampere's circuit law, we know that the closed line integral of magnetic field around a closed path is equal to current enclosed by that path. Here, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 0, we have to apply this condition. Let it be equation 1. From 0 to 1, Hn1 delta y by 2. From 1 to 2, it is Ht1 delta x. From 2 to 3, it is minus of Hn1 delta y by 2. And 3 to 4, it is minus of Hn2 delta y by 2. 4 to 5 minus Ht2 delta x. 5 to 0 plus Hn2 delta y by 2, and it is equal to I. As delta y tends to 0, the rectangular loop becomes boundary, and hence uh, the term associated with the delta y is equal to 0 Ht1 minus Ht2 into delta x is equal to I, equation 2, and Ht1 minus Ht2 is equal to I divided by delta x. It is equal to K. Let it be equation number 3. It is equation number 3, where K is the current density placed at the boundary. The units of K are ampere per meter. Equation 3, Ht1 minus Ht2 is equal to K, and based on right hand thumb rule, here K is the current, H is the magnetic field intensity. Based on right hand thumb rule, this can be written as Ht2 minus Ht1 is equal to K cross AN1. It is equation 4, where K is the free current density deliberately placed at the boundary. If there is no current density at the boundary, then the value of K will be equal to 0. And from equation number 4, we get Ht1 is equal to Ht2. This condition is valid only when the value of K is equal to 0. And a key point you are supposed to remember is you need to note equation 4. This equation is useful in solving gate problems. Equation 4 is very important in solving gate problems. Just make a note. Boundary conditions on B. Here, consider a cylinder on the boundary of two media. Delta S, it is boundary. Height of the cylinder is delta H. Once again, B1 in medium 1. This can be split as BT1 and BN1. It is the direction of BN1, and it makes an angle with respect to normal. It makes an angle theta 1 in medium 1. B2, its tangential component is PT2 and its normal component is BN2. It makes an angle theta 2 in medium 2. Now this is the direction of BN2. As we know, the magnetic field, Gauss law for magnetic fields, closed surface integral of, let it be equation number 6. From equation number 6, as delta H tends to 0, Bn1 into delta H, delta S minus Bn2 into delta S is equal to 0. Uh, that is Bn1 minus Bn2 into delta S is equal to 0. Here, delta S cannot be equal to 0. So, the term Bn1 minus Bn2 must be equal to 0. Then we get Bn1 is equal to Bn2. This second boundary condition. Law of refraction of magnetic fields. Uh, you can apply the cos theta and sin theta in the previous figures. You will get the tan theta 1 by tan theta 2 is equal to mu 1 by mu 2. Mu 1 is equal to mu naught mu r1 and mu 2 is equal to mu naught mu r2. And this can be simplified as tan theta 1 by tan theta 2 is equal to mu r1 by mu r2. And this is called law of refraction of magnetic flux lines at a boundary with no surface current. Means this equation is valid with k equal to 0. A sample problem. Here, medium 1 with z less than 0, mu r1 is equal to 6. Z is the position of boundary. Z greater than equal to 0 is medium 2 with mu r2 is equal to 4. B2 is equal to 5ax plus 8az, and the value of k, it is the current density placed at the boundary. The value of k is equal to 1 by mu naught ay cap milliampere per meter, and AN12 is a unit vector directed from medium 1 to medium 2 normal to the boundary. Here AN12 is Z less than 0, Z equal to 0, Z greater than 0 means it is taken as plus AZ cap. Now let us further proceed with next slide. K is equal to 1 by mu naught AY cap milliampere per meter, and AN12 is AZ cap. Let us apply Bn1 is equal to Bn2. Here what you are supposed to calculate is H1. To determine H1, we are supposed to calculate HT1 and HN1. From this condition, we can determine HN1. Uh, HN1 can be calculated as mu naught mu R1 HN1. Z equal to 0 means normal to the boundary is Z axis. So the normal component Bn1 is equal to Bn2 is the AZ component, 8 AZ milliampere per meter. It is equal to 8 AZ cap milliamperes per meter. Now the value of Hn1 is 8 by mu R1 is equal to 6 mu naught AZ milliamperes per meter. Now the value of Hn1 is equal to 1.33 by mu naught AZ cap milliamperes per meter. And Hn1 is over. In the next PPT, we are going to calculate HT1. To determine HT1, we are supposed to use this equation HT2 minus HT1 is equal to K cross AN12. Here K is equal to 1 by mu naught AY 10 power minus 3. It is milli AY cap. AN12 is AZ cap. Now here HT2 can be written as BT2 by mu 2 minus HT1. BT2, the value of BT2 is 5 into 10 power minus 10 into 5 into 10 power minus 3 AX cap by mu 2 4 mu naught. Mu R2 is equal to 4 minus HT1 is equal to 10 power minus 3 by mu naught. The cross product of AY cross AZ is AX cap. And from this, after simplification, we'll get the value of HT1 as 0.25 AX cap milliampere per meter. Now we can write the value of H1 as HT1 plus HN1 0.5 by mu naught it is, and it is equal to 1 by mu naught 0.25 AX plus 1.33 AZ cap milliampere per meter, and from this we can determine the value of B1 as mu1 and H1. You can multiply the value of mu1 with H1, you will get the value of B1. One practice problem: refer to the procedure and determine the value of H2. Thank you. We will meet with the next lecture.